Good morning, everyone. Thanks for choosing our educational course. And this is the first lecture of the course, which regards terminology of time-varying connectivity in resting state fMRI and an overview of the methodological framework introduced in literature so far. So first of all, what is functional connectivity? So it's defined as a measure of statistical dependence between functional signals that come from different regions of the brain. So first of all, imagine we take some regions of interest from, for example, an atlas or a parcellation. We compute the average fMRI time course within these regions, and we end up with, let's say, a couple of hundreds of these time courses, for which you see examples here. And then what we want to do is compute a measure of pairwise correlation between each pair of this time course, considering the whole length of the acquisition. So we end up with a matrix that we call functional connectivity matrix or functional connectome, which is of dimension ROIs per ROIs, and that includes indeed values of correlations between each pairs of region. We can also refer to this matrix as static functional connectivity because it has no information about temporal variation. So it considers, as we said, the whole time course, and it doesn't allow to look at temporal variations. In fact, we can say that this static functional connectivity we can consider now two main properties. One that we introduced already is being averaged, meaning that it refers to the whole length of the acquisition, and it summarizes with one measure, which can be, for example, the Pearson linear correlation rho. So during the typical length of a resting state acquisition, which could be, for example, 5 to 15 minutes, you would end up with one functional connectivity that tells you how different regions are related, but we wouldn't have access at possible temporal variations of this functional connectome. The second property that I would like to introduce is, and to point out, is that this metric is memoryless, in the sense that it's invariant to reordering of time points. What does it mean? That if you have a certain coefficient, correlation coefficient rho, then and you shuffle the time points of your time series, of course, of all regions that you are considering, then you would get the same coefficient, and so the same, again, functional connectivity matrix. So what we want to do with when we want to investigate the dynamics of functional connectivity is actually going beyond these two limits, if you want, of static FC. And if we relaxed the first property, so being averaged, then we end up with a first class of methods that we want to define today that we call time-varying functional connectivity, that yields actually really a temporal sequence of functional connectivity. So where you can appreciate temporal variation of functional connectivity. And this includes, for example, sliding window methods, co-activation patterns, and so on. Instead, if we relax the second property, being memoryless, then we have a second class of methods, which we refer to as dynamic functional connectivity, which are these methods that indeed look at the relationship between time points. So methods that wouldn't be invariant to the reordering of time points. For example, autoregressive models, ICAPs, and so on. So today we will see an overview of all these methods. So time-varying FC approaches first, and then dynamic FC approaches. And last, I would also give you a little overview of how we can actually integrate the underlying neural structure in this framework of dynamic function of the brain. But let's start with the first category of method, that is time-varying functional connectivity approaches, and with the first method, which is sliding window FC. So sliding window FC is the most commonly used, I would say, and probably also for its simplicity of time-varying functional connectivity. And so what we do is exactly as before, we consider a bunch of functional time courses, but, oops, sorry, instead of considering the whole length of the acquisition, we only consider a restricted window, let's say around 1 minute. And we compute there a measure of correlation between all time courses pairwise, and then we slide the window so we can actually see how this correlation changes in time. So what we can retrieve is a time course, the one you see here on the right, of the connectivity, functional connectivity for each pair of brain regions, of course. So in other words, time-varying functional connectivity consists in multiple functional connectomes. So one functional connectome for each window that you are analyzing. Then, I mean, we can actually analyze the temporal properties of time-varying functional connectivity in different ways. For example, the simplest way is to retrieve some measure of connection-wise variability. So connection per connection, you can compute simple metrics of, for example, variance or standard deviation to see if the functional connectivity of a certain pair changes a lot in time or not. Or you can act at the level of the matrix, and you can, in a more complex way, you can look at the graph time course. So time varying graph analysis, for which we have some examples in literature. For example, you could look at graph properties and how they evolve in time. Or if you apply some factorization techniques to your connectivity matrix, you can actually retrieve what we call connectivity states that are a number of exemplified states that the brain is going to within the time of the acquisition, and the properties of this state will be different, of course, with respect to the technique that is used to retrieve these states. For example, k-means clustering is an option, principal component analysis was used before, and so on. So from connectivity states, so you will be able to see which are the patterns that the states that the brain visits during the acquisition, as we said. You can have different properties, as we said. For example, you can have states that are exclusive in time, in the case, for example, of k-means clustering, and the one that you see here. In that case, if you project back connectivity states to the temporal dimension, you can see occurrences of connectivity states of each of the state. And indeed, what you could compute is, for example, transition probabilities from one state to the other. Alternatively, if another method was used for, that allows for states being jointly expressed at the same time point, this produces what is called in literature meta-states. So a certain combination of basic states at each time point. In this case, what you can look at is at a higher level metastate occurrences, basically. Then, of course, time-varying functional connectivity, so sliding window has certain limitations, and the first one is for sure the choice of the window parameters, which is not easy to do because it's, of course, arbitrary, and it will influence your analysis. So the first one is the window length. So what we have to consider when choosing the window length, there are many works on that in literature, is that we have a trade-off between sensitivity, so being able to see the fluctuations indeed that we want to see. So the window should be short enough to allow us to see the changes, because otherwise, if it's too long, everything which is inside the window is averaged out, right? But also specificity. So the window should be long enough to only detect real fluctuation and don't include any spurious fluctuations. And for this, a rule of thumb was introduced saying that the window should be longer than the inverse of the minimum frequency present in the original time course. So this relates to pre-processing choices of your time course. So of course, it's a choice that depends on case by case on the study and on the needs of the study. So for example, also on the frequency of the events that we are respecting, also depending on the clinical application and so on. Another choice is about the window shape. So the mostly used, I would say, it's a rectangular and simplest window, but a tapered window could be used to increase SNR, so actually to reduce the noise caused by some noisy peaks that would be given less weight with this type of window. Then another important choice that would actually influence the analysis is the choice of the parcellation, because parcellation can be based on different features. So for example, anatomical features, a functional one, a multimodal parcellation, and so on. And so on this topic, there is some effort in literature, and also what I focused on some years ago was in trying to retrieve dynamic functional connectivity without using a parcellation. So going beyond the atlas and investigating dynamic functional connectivity voxel-wise. So the idea is exactly the same. So using a sliding window, retrieving functional connectomes, but the problem is that when you work at the level of voxels, you have 100,000 voxels to consider. And so definitely you have a dimensionality problem in trying to compute or store these functional connectomes. So a workaround that we found was approximating the functional connectome at each window by its eigenvector centrality, which would be a rank 1 approximation of the matrix. So it's the first eigenvector of each connectivity matrix. And the trick here is that we can actually compute the eigenvector centrality by keeping the functional connectome matrix implicit. So we don't need to explicitly compute that. We can compute it directly from the time courses. And so being able actually to look at the variations of functional connectivity across time voxel-wise. So based on that, we introduced the first parcellation. It seems a bit funny that we want to introduce a parcellation and we just said that we don't want a parcellation, but indeed there is a reasoning behind, so which is the following. So of course we didn't want to be influenced by an a priori chosen parcellation, because you could average out something by using average time courses. But at the same time, once we reach the voxel level, so the information at the voxel level, we can also think that not probably the granularity level that is needed, it's not at the voxel, because of course, we can expect a similar behavior also in terms of dynamic functional connectivity from neighboring voxel. But what is the right granularity? So based actually on the voxel-wise results, so voxel-wise dynamic functional connectivity, we just, in a completely data-driven method, aggregated voxels that had the exact same behavior in terms of DFC, time-varying functional connectivity. And so we obtain a parcellation at two different resolutions, a long range and a finer scale, which might be more useful to analyze specific circuits in the brain, that has as advantage the fact of being completely data-driven, driven by dynamics of functional networks, so including this information, and solving this well-known issue of a priori choice of the parcellation. So this would actually solve the problem of having a parcellation, but then another category that I would like of methods that I would like to introduce you is going behind the window. So what if we don't want to use a window at all? So Let's consider our two time courses and let's take a step back so to contextualize this type of analysis. So as we said, if we do static functional connectivity, we average across the whole time of the length of the time course, and we get a picture of what we want to see in the brain, which is very blurred. I mean, not the images are blurred, but let's say conceptually, the information that we retrieve at the functional connectivity level is very blurred because it averages out all the temporal variations. The concept is exactly the same when we use a sliding window, simply that the time of the sliding window is restricted, so we average out less, and so we get still a picture that is a bit less blurred. But then what if we could actually select time frames that represents key points, so that are particularly important, and that because they capture important events, and so this would allow us not to average at all and consider a very neat picture of functional connectivity. So this is the idea behind co-activation patterns, which was introduced in 2013 and inspired by the point process analysis, PPA, that simply selects certain time points based on the activation of a seed. So it hypothesized to have a region of interest, or a seed, to select a seed in the brain, and to investigate brain patterns or functional patterns when this seed is active. So it's simply taking a threshold on a seed time course, selecting those time points for which that region is above the threshold, and then so considering the frames, the fMRI bold frames at these time points, and clustering them. For example, with k-means clustering in the original formulation of CAPS. So the cluster centroids would be the CAPS, so the co-activation patterns. The patterns that mostly occur within the acquisition while the seed is active. And with this method, so co-activation patterns include regions that recurrently co-activate or co-deactivate with the seed, but for a limited amount of time. So the difference with previous methods that we saw is that here we can also see patterns that really refer to a very short duration, events of short duration, and that in this case wouldn't be averaged out. For example, here on the left, you see the CAPS related to PCC, so the posterior cingulate cortex, and we can see on one hand that we retrieve resting state well-known networks such as the DMN, also decomposed in different subportions, so meaning that indeed these networks are not always occurring all the time as a whole, but probably different portions of the network are recurring at different moments. So this is something that you are able to appreciate just because of this analysis. But also the fact that other patterns could be retrieved may be related to short amount of times, and that couldn't be retrieved without a dynamic analysis. Another example that I would like to mention, but I wouldn't go into details since we have the luck of having here Joana Cabral that introduced this method and that will guide us through whole details in her presentation after. But I just wanted to mention it as an example of frame-wise analysis is the leading eigenvector dynamic analysis data. Here, this is a frame-wise analysis because we got rid of they got rid of the window by considering coherence connectivity. So what is computed is instantaneous phase coherence at each time point between different regions of the brain. So retrieving a functional connectome per time point, what you see here on the left. And then in order to reduce dimensionality, what they thought was, again, to consider the first eigenvector, so a first a rank 1 approximation of these connectomes that would be evolving in time. Okay, then I think we can go to dynamic approaches that, as we said, would be approaches that are not memoryless. So that indeed look at the relationship between time points. The first one that I would like to mention is a revisitation of CAPS. Since we went into details with CAPS, I think it's very good, and we have the means now to understand innovation-driven CAPS, what we call ICAPS. So where does the dynamics come from in here? It comes from the fact that it's not fMRI time courses that enter the clustering, but it's innovation signals. What are innovation signals? It's the first derivative of a denoise and deconvolved version of bold signals. These are the one that you see here in purple, and basically being the first derivative, they basically have peaks where we have a change in the fMRI time courses. So we are not looking here at what co-activates, in other words, but we are looking here at which regions change together. So they either increase or decrease their activity level at the same time. So it's a bit more general. We look at transitions of the bold signal rather than peaks. And from here comes the relationship between time point 1 and time point 2 from the derivative. These are examples of frames that enter, so innovations that enters the clustering. And this is an example of the ICAPs that are retrieved during resting state from a healthy population. So as you can see, we have a match with well-known resting state networks that we can recognize. For example, the ICAP that recurs, that has the longest duration, actually it's the one highlighted here. So it's the DMN, which makes sense. But we also can retrieve new information. So we have access to subsystems of the DMN, so parts of the DMN that occur separately. And also we are able to basically for each of these patterns see when it occurs, the percentage and the length. Okay, so another category of methods, of approaches that we can define dynamic because they look at the influence between time points is autoregressive models. Maybe the ones that by definition look at this influence since they indeed model the relationship between different time points. In fact, this is the equation of autoregressive models, and here xt is in fMRI volume at time point t, just vectorized, so with n regions. And so fMRI volumes, an fMRI volume at each time point is explained here as a linear combination of previous volumes, of actually p previous volumes, p being the model order. And the relationship between, so the dependency between different time points is encoded in this coefficient matrix A, so that contains basically the correlation between a brain pattern and the same brain pattern, but at a time point t minus L. So if you want, this represents a dynamic version of the correlation because it's the correlation at two different time points. What was shown actually from the recent or let's say the research of the latest year of Rafael, which will also give a presentation, but not exactly on that later, is that first order autoregressive models explain fluctuations of functional connectivity better than static functional connectivity, and also of hidden Markov models. And also, when trying to link static and dynamic FC, so found with the autoregressive model, with the behavioral variables, so behavioral measures on healthy subjects from the HCP, on average, dynamic functional connectivity explains more behavioral relevance than SFC. Also, based on autoregressive models, we can have a dynamic extension of component analysis such as ICA, PCA, which was again introduced by a project led by Rafael, and is called dynamic mode decomposition. So here, how do we retrieve dynamic modes, the components, simply by eigen decomposition of the coefficient matrix A. In fact, the coefficient matrix A yields complex eigenvectors with a spatial information, so spatial patterns, what we call the modes, but that are linked also to a temporal information encoded in the eigenvalues of the matrix. So each spatial pattern, each eigenvector is also related to an eigenvalues from which we can retrieve a damping time, so the time that is of decrease of this pattern, and also a period of occurrence of this pattern. So this is why we can refer to these components as spatiotemporal modes. The result shows that we have two modes that are purely real. So the first two are purely real, and they oppose well-known resting state networks. For example, the first one captures the alternance between default mode network and task positive network, so very realistic. And the second one, again, accesses subsystems of the DMN, in fact, containing only prefrontal and lateral posterior subregions of the DMN, and contrasting them to visual regions in blue. Last, I would like to spend some words on how the evolution of functional signals is supported, or how it is linked to a constant, indeed, architecture underneath, which is represented by the structural white matter, structural architecture of the brain underneath. So one method that emerged in the recent years, in the last decade, applied to the brain is graph signal processing. Also a topic where I worked, that I focused on a lot in the latest years. And so in graph signal processing, indeed, we see functional activity signals as graph signals, so signals defined on top of a graph that is represented by structural connectivity. So this is how these two information are linked. And the question is, how is function using the underlying structure? So first of all, so the graph that we consider is a structural connectome. So it's like the matrix that we saw before for functional connectivity, but includes information about physical connections of different regions represented by white matter fibers. And from the decomposition of this matrix, in particular the eigen decomposition of the Laplacian of this matrix, we can retrieve patterns that form this structural backbone that are defined as structural harmonics. So these are only based on structure. And what we do next is basically decomposing the brain activity in terms of this structural harmonics, and doing that for each time point. And what we introduced is a measure actually of structural function coupling at the node level, which we call structural decoupling index. So it allows you to quantify actually the relationship between function and the underlying structure across the brain. And what we could see is that actually there is a specific spatial pattern of this structural decoupling index going from more lower level sensory regions, which are more coupled, to high level cognition regions, which are more decoupled. Then we showed that this spatial pattern of SDI has a behavioral relevance because it relates to domains, behavioral domains, from more basic to more complex, higher level. And also what we could show more recently, so this year, is that we can perform fingerprinting and task decoding with very high accuracies based on this measure of structural decoupling index, so on structural function coupling. But so if you want more information about it, I will also give a talk more specifically on that at an early morning symposium on Tuesday. So come at 8. But so we can also ask ourselves, how does the relationship between function and structure change over time? And what was shown in this preliminary study is that for several domains, dynamic measures of structure function coupling, so specifically looking at standard deviation, instantaneous change, actually enable a significant prediction accuracy, better when it was not the case using static measures. An alternative that looks also at the relationship between structure function coupling, of course, is a very big category of that I just want to mention for you. Whole brain computational model try to simulate functional signals based on a specific parcellation and a specific structural architecture underneath. And simulated data should satisfy different criterion, so spatial validation, spectral validation, so being realistic in terms of functional connectivity patterns, in terms of frequency content, but also what I wanted to underline, a temporal validation. So functional connectivity temporal evolution is considered and should be replicated so that the functional simulated data can be considered realistic. This is it. So as a take-home message, I will be very short. We can conclude that the brain is always active and dynamic. So it's not enough to look at functional connectivity in a static way, so ignoring temporal variations. And then to investigate temporal variations, there's a plethora of methods, and the choice really depends on the specific needs of the analysis or of the project. Between data-driven versus model-based methods, for example, dynamic or time-varying, which could depend, for example, if we have to correlate with behavioral data or other modalities, and also windowless methods overcome limits of sliding window, but are still underused in clinical applications. Also, the integration of the structure is something, with the structure underneath, is something that needs to be explored further. With that, I want to thank you, everyone in MIPLAB, where I work in Switzerland, and thank you all for the attention.